Hello everyone, let's discuss Runge-Kutta methods and 2D and 3D flows. First, let's discuss the second order Runge-Kutta method. This method works in two stages to get from tk xk to tk plus 1 xk plus 1. For stage 1, we make a single Euler step from tk to produce a predicted next particle position xpred equals xk plus hu of tk xk. We evaluate the velocity field at the predicted point upred equals u of tk plus 1 xpred. For stage 2, we go back to tk, and this time we take an Euler step using the average of the velocities. U average equals a half u of tk xk plus upred. In this way, we obtain x of k plus 1 is equal to xk plus h of u average. The local error incurred after one Runge-Kutta step is of the order O of h cubed. So, after k steps, the global error should be reasonably O of kh cubed, which is equal to O of tkh squared, and so, at a fixed value of tk, the error is proportional to h squared. This is better than Euler's method, for which the error is proportional to h at a chosen xk. Now, let's discuss the Trapezium Rule. To present this method, it's simplest to discuss a velocity field which is purely time dependent, and then we'll generalize later. We solve the particle path problem dx over dt is equal to u of t with x of 0 equaling x naught. Integrating, we have that x of t is equal to x naught plus the integral from 0 to t of u of s ds. If we construct a solution at the discrete set of t points tk equals kh, for chosen step length h, we then have that x of tk is equal to x naught plus the integral from 0 to tk of u of s ds, which is equal to x of tk minus 1 plus the integral from tk minus 1 to tk of u of s ds. Therefore, x of tk plus 1 minus x of tk is equal to the integral from tk to tk plus 1 of u of s ds. Now, the range of integration is from tk to tk plus 1, which is just the step length h. In practice, this will be small, and so the integrand will only be integrated over a small range. We can approximate the integral by taking the integral from tk to tk plus 1 of u of s ds is approximately equal to a half of h of u of tk plus u of tk plus 1. This comes from computing the area of a trapezium. Using this approximation, we obtain the trapezium rule x of tk plus 1 is equal to x of k plus a half h times u of tk plus u of tk plus 1. The error incurred at each application of the trapezium rule is of the order h cubed. This rule easily generalizes to the case where we have velocity which is also dependent on x. Then the rule is x tk plus 1 is equal to x k plus a half h of u of tk xk plus u of tk plus 1 x of tk plus 1. Note that this is an implicit equation to be solved for xk plus 1. It may or may not be easy to solve for xk plus 1 depending on the problem in hand. Next, let's discuss 2D and 3D flow. For 2D, the particle path problem is dx over dt is equal to u, dy over dt is equal to v, with some initial conditions x of 0 is equal to x naught, y of 0 is equal to y naught. For a three-dimensional flow field with velocity u equals u of x, y, z, t, I, plus v of x, y, z, t, j, plus w of x, y, z, t, k, the particle path satisfies the system dx over dt is equal to u, dy over dt is equal to v, dz over dt is equal to w, with some initial conditions x of 0 equals x naught, y of 0 is equal to y naught, and z of 0 is equal to z naught. In vector form, a succinct way of expressing these is dx over dt is equal to u with x of 0 equal to x naught. Note that in each case, we have more than one equation to solve simultaneously. The numerical methods we have discussed up to now extend to more equations in the intuitive way. For a general dimension, Euler's method becomes tk equals k h xk plus 1 is equal to xk plus h of u tk xk for k going from 0, 1 to etc. For a general dimension, the second order Runge-Kutta method becomes xtemp is equal to xk plus h u tk xk, and then evaluate u temp equals u of tk plus 1 xtemp, and then xk plus 1 is equal to xk plus h over 2 times u of tk xk plus u temp. And as ever, thank you for watching.